In this session, let us see how the torque angle delta is more than 90 in induction. Okay, basically, in my previous session also I told you, in the DC machine delta will be 90 degrees torque angle. Okay, and in synchronous machine delta will be 0 to 90 degrees. Okay, and in induction machine 90 to 180. How that delta angle is coming, let us see. And now in this session only you will understand one more thing, that as a generator, synchronous generator is popular. As a motor, induction motor is popular. Induction generator, in very special cases we may use, but it's not popular. Why? You will understand after this session. Okay. Now, for example, as I told you previously, in induction machine means that rotor only will be analyzed. Stator analysis will not be done. From stator, what will come? Once you connect to the stator three-phase supply, RMF will be formed. Okay, so from stator side I need only one thing, that is RMF. Okay, now let us see. This is stator and this is A and this is B and this is C. Okay, so this is A conductor, A dash will be here, and this is B, B dash will be here, and this is C, C dash will be here. Okay, so the moment I supply three phase here time displaced currents will flow IA, IB, IC. Okay, such that at any instant IA plus IB plus IC equal to 0. So if IA is like this, IB will be 120 degrees, IC will be 120 degrees, such that at any instant IA plus IB plus IC is going to be 0 at any instant. Okay, now because of this stator structure, what will happen means my poles will be formed. Okay, and that poles will be rotating with synchronous speed 120 F by P. Okay, rotation of RMF. Now let me think of my rotor is here. Okay, so in my rotor I am going to have many conductors. Okay, now basically in the rotor, if the rotor is open circuited, rotor winding is open circuited, under that condition though voltages are induced but currents will not flow. Okay, when currents will flow, when rotor conductors are closed, like squirrel cage for example. Okay, if it is squirrel cage, cages will be like this. Okay, conductors will be like this. These are all the conductors. So these conductors will be connected like this. At the end rings will be there. They are short circuited. Okay, or if you think of phase wound rotor also or slip ring rotor also, the same thing will happen. Anyway, about that we will see later. Ultimately, my rotor winding is closed. If rotor winding is closed, already voltages are induced here, automatically currents will flow or not? Yes. Okay, so means basically my rotor MMF or rotor flux will be created because of induced voltage or currents. Okay, now see here voltages are going to be induced, and here where you are going to get maximum induced voltage in these conductors. Now let us apply right hand rule. Why? For induced voltage. Okay, so induced voltage you have to apply right hand rule. It may be motor or generator. Yes, it is a motor. Okay, we are discussing about the motor, but still induced voltage only, so we have to apply right hand rule. Okay, now if you sit in the rotor, my flux is flowing from here to here. So my flux is flowing from here to here. Okay, here to here, and my pole is getting rotated in this direction. In this direction means that equivalently my conductor is rotating in opposite direction. Okay, so my flux is here, my current is here, my flux is here, and my conductor motion is in this direction, thumb. So my induced voltage is going to be cross here. Induced voltage is going to be dot here. Okay, so induced voltage here is going to be cross, induced voltage here is going to be dot, which are nothing but maximum voltages. Okay, so this is going to be maximum voltage position. Now when maximum currents will come, because depending upon maximum currents only you are going to get RMF, rotating magnetic field. It's not because of voltages. Now, as of now, voltages can be maximum. As of now, where currents will be maximum, that will be decided by rotor resistance and rotor reactance. Okay, so let us consider, for example, if rotor resistance is 0, reactance is non-zero. If rotor reactance is 0 and rotor resistance is non-zero. If both are non-zero, we have to analyze. Okay, then you will understand, why induction motor, as an induction generator, why it is not popular. One of the point we will see here. Okay, for example, as of now, means let me consider in the rotor. In the rotor, for example, rotor is having rotor resistance non-zero. Okay, for example, rotor reactance is 0. Rotor reactance is 0. Reactance is because of leakage, reactances will come. More about leakage reactances I will discuss in detailed course. Somehow leakage will be there. That leakage will be modeled with the inductance. Okay, just keep that point in mind because this is simplified course. Okay, so rotor resistance is non-zero, rotor reactance is 0. Under that conditions, rotor resistance is there, reactance is not there, means that voltages and currents will be in line or not? Yes. Okay, so if rotor currents are in line with voltages, see here, means here the moment rotor voltages are maximum, rotor currents also will be maximum. Now one problem will come. In motor, induced voltages and currents, all of you have to focus here. Induced voltages and currents should be in opposite direction. Okay, previously we discussed in basic concepts. Okay, now if it is cross, my cross is the induced voltage, my currents will be cross or dot. They will be cross only. Because, for example, let us think of transformer. In transformer, this is transformer. My induced voltage is E1 here, induced voltage is E2 here. Okay, so my current is entering into plus terminal of induced voltage such that this will absorb power. Okay, but my secondary is going to behave like generator because it is generating to the load. Okay, so that generated power here, because I2 will be coming out of positive. So secondary is going to behave like a generator, but that generated power will be absorbed in the load. But here that generated power is being utilized to convert it into mechanical form. Okay, so means transformer secondary is nothing but rotor in induction motor. So here currents are going to be dot only, currents are going to be cross only, these are going to be maximum currents. Maximum currents. Now see here, let us think of how many number of phases will be there in the rotor, because for this small thing also 2-mark question came. Okay, for example, in this, how many poles are formed from the stator side? 2 poles. Okay, now when the pole is here, how much is the induced voltage here? Maximum. When pole is here, how much is the induced voltage here? 0. How much is induced voltage here is 0. So for example, this conductor and this conductor is having back-to-back connection. Okay, so this conductor red back-to-back connection, this conductor it's closed. Okay, because rotor should be closed, rotor should be closed, otherwise currents will not flow. Okay, so for example, A, or maybe, okay, don't think of this A, B, C, means in the rotor this is phase A, this is A dash. Now if you think of from here to here, induced voltage here is maximum. When induced voltage here is maximum, induced voltage here is 0. Okay, means that this voltage and this voltage is time displaced by 90 degrees or not? Yes. For example, this conductors are not there. For example, now I'm going to have this back-to-back path is this back-to-back path is this. Only 2 coils or 2 turns let us consider. Under that condition, how many phases are being developed? Whenever this is positive maximum, whenever okay, so whenever this is positive maximum, this is going to get 0. So this another voltage is 0. Okay, whenever this voltage is maximum, this voltage is 0, so 2 phases are not? Yes. Okay, now how to calculate number of phases in the rotor? Number of means, as I told you, very soon I will solve gate question. Okay, they asked this. For example, this are not there. Okay, so one phase, second phase. Now this phase voltage and this phase voltages are displaced in time by 90 degrees because these turns are displaced in space by 90 degrees because this is going to be MMF, and similarly this is going to be MMF. Means that this MMF and this MMF is space displaced by 90 degrees or not? Yes. Okay, so one MMF is like this, another MMF is like this. So MMF is displaced by 90 degrees. What is space displacement of the winding? In our previous session we have seen. Okay, in basic concepts, MMF, axis of MMF of different phases, different windings should be displaced in space. We call it as space displaced winding. Now see here, how many slots are there here? 1, 2, 3, 4. 4 slots are there. Now in this, how many poles are there? 2 poles are there. How many phases are there? 2 phases are there. So slots per pole is nothing but number of phases in our squirrel cage rotor. About phase wound rotor we will see later. Okay. Anyway, see here. For example, if I have here conductor, here also let me consider conductor. Now this induced voltage is maximum. This induced voltage is 0. This induced voltage will be some less than maximum, more than 0. This is negative maximum, for example. This is less than negative maximum but more than 0. So this voltage and this voltage is time displaced by some angle. What is the angle? 45 degrees. Okay. Now for example, if I have all these slots, okay, how many slots are there? 1, 2, 3, 4, 5, 6, 7, 8. 8 slots are there. Per pole, how many slots are there? 4. So my rotor is going to develop 4-phase system. 4 phases. Forget about all. Number of slots per pole is nothing but number of phases created in the rotor. Okay, so people may be confused, it should be 3 phase only, it should be 8 phase only. It is not like that. Number of rotor slots per pole. Slots per pole is nothing but number of phases in squirrel cage rotor. Forget about it. Now coming to the point, see here, as of now maximum currents are happening here. As of now 0 currents are going to happen here. As of now some positive currents are going to happen here. So this current and this current is time displaced or not, because these two windings are space displaced. Now because of all time displaced currents flowing through all space displaced winding, one resultant MMF will come. That resultant MMF should be aligned with the phase axis in which maximum currents flow. Where maximum currents are flowing? Here only. So because of all these currents, one resultant MMF will come. That resultant MMF is aligned with the phase axis in which maximum currents flow. Cross here, dot here. So my rotor MMF is this. Where is my stator MMF? N to S. Stator MMF is this. Okay. So what is the angle between stator MMF and rotor MMF? 90 degrees is going to be the delta. Okay. Now some may feel in synchronous machines, I said that delta should not be stator MMF to rotor MMF, but it should be rotor MMF to resultant MMF, I said. Okay, but now I am saying load angle is nothing but stator MMF to rotor MMF. Why? Because in our synchronous machine, stator MMF is coming, rotor MMF is coming. Because of interaction of stator MMF and rotor MMF, one resultant MMF is coming. But here resultant will not come because, for example, stator MMF is there. Okay, rotor MMF is there, but that rotor MMF or rotor ampere turns or rotor flux will be automatically killed, and again only stator flux only will be there, in the air gap. Armature reaction is not there. So means my resultant MMF or resultant flux is going to be this only. Okay, so means for example, load is not there. This is going to be the flux. Even when load is there also, this particular flux will be automatically killed from stator side by taking extra compensating currents, such that my resultant is going to be this only. Okay, so even now also I am saying means the torque angle is nothing but rotor MMF to resultant MMF. Okay, but where is resultant MMF? Resultant MMF is nothing but stator only because rotor MMF is going to be killed. Now let us see if it is having rotor reactance. I have taken here A, B, C. For these three, phases are connected. Okay, stator is connected with the supply source. And for example, this is stator pole created, and which are rotating in this direction with ns or omega s. Okay, now you are going to have rotor here, and this rotor I am going to have conductors all over, slots. Okay, those conductors are short circuited or maybe somehow connected. Okay, closed circuit. Now what will happen means, in this case let me consider rotor resistance is not there, but rotor reactance is there. Rotor reactance is non-zero. Okay, so resistance is 0 but reactance is there, means that my current should lag behind voltage by 90 degrees. Okay, anyway, like the moment same, like here induced voltage is going to be cross, induced voltage is going to be dot, this is going to be maximum induced voltages. Okay, now let us think of where maximum currents happen. Why maximum currents are important? Because depending upon maximum currents only, my net resultant MMF will be aligned with the phase axis of that. Now see there, all of you, as of now induced voltage is maximum. Now in order to get maximum current here, as of now induced voltage is maximum, in order to get maximum current you have to wait for 90 degrees because current lag behind voltage by 90 degrees. Now as of now voltage is maximum, in order to get current maximum I have to wait for 90 degrees. By the time it will go like this, 90 degrees. Okay, so because space and time and space both are same. Okay, so as of now voltage is maximum, in order to get current maximum you have to wait for 90 degrees, means that by the time it reach current maximum, pole will reach here, or when pole is here current maximum will occur here. Okay, so current maximum is going to be occurring here. So this is cross, this is also cross only, dot only, so these are going to be current maximum. If it is current maximum is like this, cross here, dot here. Okay, cross here, dot here. Okay, because my resultant MMF created in the rotor because of rotor currents. My rotor MMF, net resultant MMF, is going to be aligned with the phase axis in which maximum currents flow. So cross here, dot here. So this is going to be rotor MMF. Where is my stator MMF? Stator MMF is this. Okay, so rotor MMF, stator MMF. What is delta here? 180 degrees. Okay, now like in order to produce continuous electromagnetic torque, number of poles of stator and rotor should be same, fine. We'll see about that later. And second thing is, my stator MMF and rotor MMF should be stationary with respect to each other, and then they should be displaced by non-zero displacement angle. But now, for example, if I think of rotor, my rotor flux is coming out. You are sitting in the air gap, so it should be N pole of the rotor, this should be S pole of the rotor. So N, repulsion will be there, repulsion will be in this direction. S, repulsion will be there in this direction. You are sitting at the shaft. Okay, so some torque is coming, pushing in this direction, some torque is pushing in this direction. What is the net resultant torque appearing here? 0. Okay, so in this case electromagnetic torque developed is going to be 0. Okay, let us think of in my previous session. Okay, with our rotor resistance is non-zero, rotor resistance is there, reactance is not there. Now if you see, okay, here if you sit in the air gap, my rotor MMF is coming out of it. So this is going to be north pole of the rotor, this is going to be south pole of the rotor. Okay, north will be attracted to south, south will be attracted to north. Means that because of this attraction, torque developed will be in this direction, electromagnetic torque. Because N pole, S pole, interaction will be there. So torque is developed in the same direction of RMF. RMF was rotating in this direction. My electromagnetic torque developed is also in the same direction. Now, if I see here, there is no torque developed. For example, let us consider if rotor is having resistance also and reactance also, what will happen? In the sense, rotor resistance also let me consider, rotor reactance also let me consider. Let us see, this is going to be stator. A, B, C. Okay, let me supply three-phase supply to this. So because of that, from the stator side, I am going to get N pole of the stator, S pole of the stator, which is, for example, rotating in this direction with synchronous speed ns or omega s. Okay, now let me think of rotor. Now my rotor is let me have many conductors here. Okay, as of now maximum voltage are induced because pole center, so this is going to be cross here and this is going to be dot here, so this is going to be maximum voltage or not? Yes, maximum voltages, induced voltage of course. Now if you think of currents, see here resistance is there, reactance is also there. So if I think of voltage like this, current should be lagging behind it, by less than 90 degrees because resistance is there, reactance also there. Now see, as of now voltage is maximum here, as of now voltage is maximum in the rotor when the pole is here, and in order to get current maximum you have to wait for some time. By that time rotor pole will go here. Now when rotor pole is here, current will be maximum here. Okay, when rotor pole is here, current maximum will come here. Okay, so somewhere here current maxima is happening, current maxima. Okay, so this is going to be current maximum. Okay, so this is going to be cross, so this is going to be cross, this is going to be dot, so this is going to be dot. Okay, let us think of my resultant MMF. Okay, sorry, from rotor MMF. So rotor MMF is going to be cross here, dot here, cross here, dot here. So my resultant MMF is going to be here, FR, rotor. Where is my stator? N to S, stator MMF. What is the angle between here to here? Is more than 90. Okay, so delta should be more than 90. Now let us think of how pole formation, like if you sit in the air gap, MMF is coming out. If you sit in the air gap, flux should come out. So it should be north pole of the rotor, it should be south pole of the rotor. Now N repulsion will be there, S repulsion will be there, and S attraction will be there, N attraction will be there. So torque will be developed in this direction. Okay, so if my stator RMF is rotating in anti-clockwise, my torque also is developed in the same direction. Means that it's a motor. Okay, because means electromagnetic torque, and of course if I release it, for example I strongly hold the rotor not to rotate, then I am going to have twisting moment in anti-clockwise direction or not? Yes, if I release it, it will be accelerated in the same direction. Okay, now what is the conclusion from here? The conclusion is, if rotor resistance, for example in my first session, rotor resistance is existing, reactance is not there, torque is developed or not? Yes. For example in this, resistance is also there, reactance is also there, torque is developed or not? NS pole interaction, yes. But if I have only reactance and if I don't have rotor resistance, torque developed will be zero. What does it mean? Is it possible to develop the torque without having any rotor resistance in induction machine? No. Okay, so point is very clear here. For example, in ideal case of DC machine, generator motor, how much will be the efficiency? 100%. Okay, if you think of, for example, ideal case of synchronous machine, how much is efficiency? 100%. If you think of ideal transformer efficiency, 100%. But if you think of ideal induction motor efficiency, it will be less than 100%. Why? Rotor should have resistance. If rotor is having resistance, then only torque will be developed. Okay, so even in ideal conditions of induction machine, rotor copper losses, rotor resistance will be there, rotor currents flow, because of that rotor copper losses should be there. Okay, so even in ideal conditions of induction machine, efficiency should be less than 100%. Because means, like if they don't give some data in your question, if they don't give about stator core loss, neglected. If they don't give something about mechanical losses, neglected. If they don't give something about stator copper loss, neglected. But if they don't give something about rotor copper losses or rotor resistors, you have to find it, because without calculating or without having rotor copper loss, okay, means torque will not be developed, means that even in ideal conditions of induction machine, efficiency is less than 100%. So compared to synchronous, induction machine is more lossy or not? Yes, induction machine is more lossy. But so that's why actually as induction generator failed to meet the expectations. Okay, our synchronous machine alternator is very much popular. Why? Because induction generator is lossy. Okay.